Welcome everyone to the amplitude session. As a first talk, we will have Oliver Schlotterer, who's going to talk about higher-genus Riemann surfaces and string amplitudes. Please, Oli.
Uh-oh, that's not so easy. Can everybody hear me? Yeah, thanks a lot, Hinek, for the kind introduction and also for agreeing to speak later on. Welcome to the strings parallel session, and I will try to give a gentle kickoff with an update on higher-genus Riemann surfaces and integration thereon. And as you can guess from the interesting title, it is meant to be an example where string theory and string amplitudes try to do something for other fields. So I hope that I can deliver some results of relevance beyond string amplitudes themselves. Namely, the slightly broader context in which I'm trying to get is integration in perturbative QFT and string theory. I mean, when going to amplitudes conferences, then people from different subfields are all sweating with their integrals. Let it be QFT when it's about Feynman integrals for particle physics. Also, perturbative gravity is recently wrestling with elliptic curves and Calabi-Yaus. And clearly, string theory has traditionally a couple of integrals on the homework list, where in string amplitudes, the geometry is particularly obvious. Namely, by the perturbative expansion of string amplitudes in the coupling, the tree-level contributions is governed by integrations on a sphere. And as you go to H loops in string perturbation theory, then you have, almost by definition, a Riemann surface of genus H to deal with. Yeah, but these Riemann surfaces are not only showing up in string amplitudes, but also they are everywhere in Feynman integrals, where it's slightly less obvious which Feynman graph corresponds to which geometry. Here are just two case studies as a motivation. For instance, this two-loop sunrise diagram with internal masses has a hidden geometry of a torus, and it's quite non-trivial to see that torus. And if you go a little bit higher in perturbation theory, this non-planar double box here with up to 7 different internal masses has a hidden genus 2 Riemann surface in it. So to work out the functional dependence of these Feynman integrals on masses and momenta, you need to have some experience on doing integrations on geometries like this and that. So the goal of the talk is to use string theory as a tool to become more fluent in doing these integrations systematically. So for each geometry separately, we want to have a good function space, which should ideally close under doing integrations over the marked points. So if your function space has this property to close under integration, then you have some sort of trivialized the problem of integrating over the points. So you just grab the member of that function space, which is defined to be the result of a given integration. So clearly, this sounds borderline tautological. This function space shouldn't be too large to have some meaning at all. So these function spaces should also be small enough. We need the smallest function spaces for each geometry that close under integration. And we furthermore want to have some control over the properties, such as functional relations or numerical evaluations. There are many different criteria on when you can claim victory to have a function space under good control. And the goal for this talk is to show an explicit construction of such a function space for Riemann surfaces of arbitrary genus H. And if I have time to talk about properties like functional relations, then you will hear towards the end of this talk about so-called Fay identities, which are, so to say, a driving force not only to derive functional relations, but also to double-check that we really close under integration, which is, say, the basic requirement on these function spaces. Now, the connoisseurs of Feynman integrals know that Riemann surfaces are not the end of the rope. There's impressive work on identifying K3s, Calabi-Yau threefolds, and much more in more advanced Feynman integrals, and I won't have anything to say on those. But I still believe that Riemann surfaces are a key stepping stone, because all these higher dimensional algebraic varieties, they fiber in Riemann surfaces, so there is a lot of recycling to be explored in the future. So let's for now focus on the Riemann surfaces and then do the transition to higher dimensional varieties later. Okay, to be semi-concrete about these function spaces on Riemann surfaces, let's look back at the polylogs for genus 0 and 1. So here is in red the explicit formula for the polylogs on a sphere, which are recursively defined here. So the gadget on the right has fewer entries than that on the left. So if you expand things out, then you will see that polylogs are defined as an iterated integral between 2 points on the sphere. One of them can always be set to the origin by translation invariance, and we keep the upper endpoint of the path arbitrary. So this z is, so to say, the chief variable that this polylog depends on. So looking at this slightly more abstractly, we have an alphabet of integration kernels, here a simple rational function, and polylogs are the iterated integrals on that alphabet. So this slightly more abstract viewpoint goes through immediately to genus 1. So now we are on the torus rather than the sphere as we stare at the blue formula. So also elliptic polylogs are given by iterated integrals. So again, the gadget on the right has fewer entries than that on the left. And at the end of the day, you get an iterated integral over slightly more general functions, no longer a rational one, but some kernel G, which, lives on almost the torus, strictly speaking on the universal covering space. But you just need to switch gears what you mean by integration kernel. And having an alphabet of integration kernels defines the entire function space. Okay, now what is not obvious from these definitions, why these function spaces close under integration? Well, not only in that upper variable, but also you can integrate with respect to any of these additional points, A, points on the sphere / on the torus. So for that, you need a refined analysis and you need some functional properties of these integration kernels. And clearly, you need help from math. So we were blessed in amplitudes that there were a lot of mathematicians open to reach out and to help us with all these integration challenges and to enlighten us about the Hopf algebra structures and more that are underlying these polylogs here. Okay, so these are the case studies at genus 0 and genus 1. And the obvious question is how it goes on at higher genus, 2 and beyond. What's the analog of the integration kernels? And this is clearly a question of a bigger ambition and scope. And it turns out that string theory can help if you ask a way more narrow and more modest question. Namely, in string amplitudes, you could be after a good function space for multi-loop string amplitudes. Ideally a universal one that doesn't depend on the details of the theory, whether they're SUSY or not, whether we are bosonic, heterotic, and whatnot. So what I mean by a function space for string amplitudes is the following. As explained at the beginning, an H-loop string amplitude with n external legs will be given by some moduli space integral. Moduli space of Riemann surface with n punctures and genus H. And what you integrate is a business of conformal field theory. And what you can say straight away is that you will have this Kober-Nielsen factor here, some exponential of the Mandelstam's in alpha prime, which involves the bosonic Green's function as a ubiquitous factor. You don't need any computation to foresee that that one is there. But the quest for the function space concerns all the rest, which is not covered by the universal Kober-Nielsen factor. Okay, and the overarching message in this talk is, by asking about a good organization principle for this function space here, you automatically solve a bigger problem, namely how to engineer polylogs on higher genus surfaces. Okay, so that means that string amplitudes can be used as an engine to set up iterated integrals for higher genus, and those in turn, as we hope, will radiate to further other fields. And I'm sure this fruitfully resonates with a lot of talks we are hearing on this conference. My apologies to those that I forgot. Okay, so just to recapitulate, these function spaces informed by string amplitudes, these are rational functions at genus 0. So that's a way to post-dict that the genus 0 polylogs are actually good definitions. Then at genus 1, you have certain combinations of data functions here. And this was actually, for me, the first time that I saw a Kronecker-Eisenstein kernel, actually in an exciting project with Carlos Mafra, where we looked at 6.7.8 points for one-loop string amplitudes, and we realized that certain objects, G2, G3, G4, are necessary to accurately describe the function space. And these were indeed the ones that mathematicians just started to use for elliptic polylogs. Okay, and it's for these G kernels, or a variant that I will introduce in a second. It's their generalization to higher genus, which will be delivered as the main result of this talk. Okay, so this is introduction and context. Is there an immediate question on all of this? Good, then I start with review at genus 1, and then go step by step through what can be said about higher genus. Let's see whether we make it to the end. So it's time to give you the definition of these genus 1 integration kernels, these mysterious GK objects. A neat way of defining them is through a generating series, a ratio of Jacobi theta functions. It's strictly speaking the odd one, this theta 1, which vanishes at the origin, and in fact an entire lattice that knows about the periodicities of the torus. And we do something slightly perverse here. We have two variables, z and eta, that look like they are both wanting to be marked points, but one of them is degraded to a bookkeeping variable. So here on the right-hand side, we are doing a Taylor-Laurent expansion in the eta variable. So it's not really appreciated as a marked point on the torus, but just used to define a couple of kernels, G1, G2, G3, being a certain order in this eta expansion. Okay, so this is one way of dealing with elliptic polylogs, but you can criticize that these G's are not really living on the torus, because they are plagued by monodromies as you go around the B cycle of the torus. So they are not yet single-valued, and, well, I guess string theorists might be a little bit more picky about that. If you want to see a single-valued version of these G's that really lives on the torus, then you can use a cheap trick and put an exponential here into the generating series. So this exponential up here is a cheap way of removing these B-cycle monodromies, and actually to all orders in eta. Good, so these are the kernels that will be generalized to higher genus, but let's be honest, we have just given up meromorphicity. And maybe that's an instance of a more general tragedy in life, that quite often you can't reconcile meromorphicity with double periodicity on the torus. Say, if you're after functions with poles, then you need to go all the way to Weierstrass with a double pole, but you can't really get a simple pole into a doubly periodic and meromorphic function. So this general phenomenon also shows up here. By the way, these generating series will play a key role in Andre's talk, so let's make sure that the definitions here stay on the board for the next hour or so. We will hear more about the importance of these Kronecker-Eisenstein series for cohomology considerations at genus 1. Okay, I could tell a little bit more side stories about these F kernels, but okay, they are definitely useful in a couple of areas. But let's get back to the main thrust of this talk. So you just got to know these Kronecker-Eisenstein kernels through certain theta functions, which is neat and explicit at genus 1. But to be honest with you, I don't know how to generalize this formula here to higher genus. At least not in a good way. I mean, theta functions at higher genus exist, but they are slightly more difficult to tame. So I won't attempt that. No higher genus theta functions in this talk. But instead, I will now give you an alternative description of these Kronecker-Eisenstein kernels, which generalizes surprisingly smoothly. Namely, these Kronecker-Eisenstein kernels can all be pulled out of the bosonic Green's function. So this expression I hope many of you recognize from studies of Polchinski or Green-Schwarz-Witten. This is the doubly periodic way of writing down a logarithm on a genus 1 surface. Sorry if the blue is not that visible. So I already told you about these bosonic Green's functions, which are overall spectators in string amplitudes. And the very same Green's function can be used as an alternative construction of these Kronecker-Eisensteins.
So can you just tell me what's in blue and baseline?
Oh, I'm sorry. This just says bosonic Green's function, and it behaves like a logarithm of the absolute value square. Okay, so F1, the first subleading kernel, is just the z derivative of the Green's function, and all the higher ones are convolutions of Green's functions and lower order f. So this is a recursion relation which generates all the f's for you, even if you don't know about this ratio of data functions over there. And this also has further advantages, such as manifesting their modular properties. And it's exactly that Green's function viewpoint on the Kronecker-Eisenstein kernels which generalizes quite well to higher genus. So most of all, I should tell you what this Green's function is at higher genus. And okay, an explicit formula would involve some prime forms, and it would take me on a long detour into the function theory on higher genus surfaces. So I will instead give you an indirect definition through the defining properties. So what a bosonic Green's function is doing for its living, it should be single-valued, a function of 2 points on the surface. It should be symmetric under exchange of the 2 points, x and y. And it should still behave like a log. So behaving like a log can be written in differential form, namely having a delta distribution in the Laplace equation. And there is a last condition, which concerns the zero mode. You may consider shifting the Green's function by a constant, or by a function of fewer variables. So there is a zero mode condition that it integrates to zero. And well, at genus 1, it's clear what I mean by integrating to 0. There is a preferred volume form given by d squared z at genus 1. But at higher genus, this requires a little bit more care. There is a particular volume form, kappa, out of many others. With respect, you can impose a normalization condition. So this is the so-called Kähler form. And the Green's function is engineered such that it integrates to 0 with respect to the Kähler form, but not necessarily to others. Okay, so this Green's function here also has the nickname Arakelov Green's function if you do these choices like that. And luckily it was studied very well in the recent string theory literature. Oh yeah, there was a beautiful work of Rodolfo, which I should have put here as well. So there are a lot of results on this Arakelov Green's function that one can capitalize on in the near future. Okay, so we are halfway there to get higher genus integration kernels. Now, there is one more thing, which also has no immediate genus 1 counterpart. What are the abelian differentials? Well, that's an easy story at genus 1. There is dz as a unique holomorphic differential form. But at higher genus, there will be multiple such abelian differentials. So this is a first example of an index notation, which is there throughout the talk. So whenever you see capital letters like I, J, K, you can assume them to be indices that run from 1 all the way to the genus H. So there are H such abelian differentials. That's why we have an omega with an index sub I. And those are characterized, for instance, through their periods along the homology cycles. So we traditionally normalize them such that the A cycle integral is a Kronecker delta, and then their B cycle integral is giving you complex structure moduli. Maybe a slightly redundant description starting from genus 4. But yeah, these periods omega over the B cycle can be viewed as representing the complex structure moduli, or the shape of the higher genus surface. So what is sloppily denoted by tau on the board will generalize to these period matrices omega. Okay, then I can, for instance, tell you what this mysterious Kähler form is from the previous slide. This is a certain bilinear in omega and its complex conjugates with an index contraction involved. So as usual, Einstein summation conventions for repeated indices. Okay, so this is how the story about the abelian differentials omega connects with the Arakelov Green's function that you saw on the previous slide. Okay, all the Lego bricks are in place. Now we can go on and construct things out of them. So first of all, the derivative of the Green's function, this was the genus 1 integration kernel F1. So let's repeat that. Let's again put the derivative of the Green's function in. which, by the way, has a simple pole for x minus c. So connoisseurs of polylogs know that it's really important to integrate over simple poles. But now we have a zoo of different volume forms, as I alluded to before. You can take bilinears in these abelian differentials and freely vary the upper index j for the anti-holomorphic one and the lower index I for the holomorphic one. There is a h by h matrix full of volume forms. And we only have one normalization joker on the Arakelov-Green's function. It usually doesn't integrate to 0. Only if I put the privileged Kähler form kappa here. Only then it will. So that's morally the reason why you should better put in such a convolution here into the first instance of the integration kernels. So this term here has no genus 1 analog, simply because you automatically run into the Kähler form in case of genus 1. Okay, so this is, if you wish, a recursion start to generate an infinite tower of integration kernels for higher genus, which, as I claim, generalize the Kronecker-Eisenstein friends at genus 1. So let's mimic what happened at genus 1. Namely, there was a recursion with convolution against the Green's function. Getting f2 is a matter of integrating f1 against Arakelov-Green's function. And we just repeat that as literal as one can ever do that at higher genus. And the new feature is indices. Well, you already saw that the f1 at higher genus has 2 indices. Again, they are all running from 1, 2, ... all the way to h, the genus. And now we get more and more indices whenever we convolute against the Green's function. Because a proper convolution will also involve a anti-holomorphic form degree, and we need an index to represent that. Okay, so this is a recursion to generate an infinite tower of such tensorial integration kernels. By construction, if you specialize to genus 1, you are back to Kronecker-Eisenstein, but you can apply this freely to arbitrary genus, even if you're at genus 4 and higher, where the Schottky problem makes certain other moves inconvenient. Okay, so then let's see how this gives rise to polylogs. So once we have all these integration kernels in place, it's not a big deal to generate polylogs from that. Step 1 is to build a flat connection. This may sound a little bit trivial. If you're used to working with meromorphic ingredients, then more or less anything you can write down is a flat connection. But not so with this non-holomorphic part, which these single-valued kernels involve. So to get a flat connection, you first of all have a dz bar piece, and that one we decorate with a non-commutative letter bi. And then we need an infinite tower where all the f kernels are sitting. I guess this is the more obvious part of the construction. And there are more non-commutative variables in place. Namely, there's a little a, which you can view as a bookkeeping variable for a cycles, and there's a little b, which you can view as a bookkeeping variable for b cycles. So this flat connection is in a Lie algebra with 2 H generators. And, well, the credit to this idea belonged to Brown and Levin. Sorry that they're not appearing right now, but already at genus 1, it was the work of Brown and Levin who taught us how to use these non-commutative variables in a beneficial way. Okay, so here is a flat connection that contains all the integration kernels that I just introduced. So let's now build iterated integrals from this. And again, it's convenient to do this with generating function. So let's take the path-ordered exponential of this flat connection j, which is defined to have all these iterated integrals over j. And be careful about the relative position of the left j and the right j, because all of them are full of non-commutative variables. Okay, maybe it's getting disturbing how often I say non-commutative. Now it's time to get rid of that. Now we expand in words in these non-commutative variables, and the polylogs at higher genus are the coefficients for all of these words. So in the formula here, you see some examples up to word length 2. And as long as you really keep all the terms in the flat connection, you're guaranteed that these iterated integrals are homotopy invariant, namely, they only depend on the endpoints, x and y, and not on the choice of how you get there. Only the homotopy class matters, so that's the reason you can sell this as a function of the endpoints and not a function on the space of paths. Okay, so this is a construction in 2 steps of the higher genus polylogs. And in the remaining 0 minutes, I would be telling you more about certain consistency conditions and arguments why they close in under integration. But in view of the timing, let's leave this for private chat. So all this to say, there is some follow-up work with Eric Doker from July of this year, where we explain why these higher genus polylogs here pass a lot of consistency checks and how to algorithmically find their primitives, not only in the x and y variables, but also in this other mark point P. Okay, let's jump to the conclusion. So the motivation of the talk was that there are a lot of nasty integrals throughout perturbative physics. And the goal is to have a unified framework to do integrals not only in string theory, but also in QFT and perturbative gravity. And the claim is that higher genus polylogs will be an essential part of such a universal integration toolkit. So you saw an explicit construction of polylogs on Riemann surfaces, regardless of their genus. And yeah, well, the missing part was to elaborate more on functional identities. Okay, that's it. Thanks a lot.
Hello? Yes, thanks, Ollie. Do we have questions? Yeah.
Thank you, Ollie, for the usually beautiful talk. At a certain point, you would also like to integrate over the moduli of the surface, right?
Oh,
to obtain
absolutely.
amplitudes.
Yeah.
Are there already methods to do that beyond genus 1? I mean, I know there are some results at genus 2, but say that I took your results at genus 3, I take some of these polylogs and I want to integrate them.
Absolutely. Yeah. Great question, and I'm sure this will keep me very busy over the next year and possibly more. Yeah, I guess step 1 to integrate over the complex structure moduli is to study the differential structure if I differentiate with respect to the period matrices. Or at genus 4, this needs to be refined to be a differential in the complex structure moduli. Yeah, so this we started to study. There's a CFT method which does this very neatly, known as complex structure deformation. So whatever you want to differentiate, you interpret it as a correlation function. But then to this correlation function, you add the stress tensor of the CFT. And you need to study how the action of the stress tensor on all these F tensors looks like. So yeah, this works surprisingly well. These F tensors are in a very loose sense closing under this complex structure variation. And yeah, I think that's something within reach for the near future, to study the differential in the period matrices. Say for the polylogs themselves, for their A and B periods that generalize elliptic multiple zeta values, and also for modular graph forms, or at higher genus they will become tensors. So this method is particularly good to differentiate modular graph tensors. And I think the first successful instance of that is what Rodolfo did to the Chang-Kawasumi invariant already in 2014. Yeah, talk to Rodolfo to learn about stress tensor insertions.
We have time for another question.
Maybe just a curiosity, is this already being applied to the final integral motivation? I mean, what is
Oh, that's underway, yeah.
underway?
Mm-hmm. So the tough part is to make contact with the polynomial description of the surface. Let me make a cheesy genus 1 analogy where the elliptic curve can be brought into this form. And in Feynman integrals, it's particularly natural to study iterated integrals over this and that. And it's a non-trivial dictionary to go from here to the universe of Kronecker-Eisenstein kernels. So this has secretly a Weierstrass function built in, which in turn is given by the derivative of f1 plus some constant. So it's non-trivial to go back and forth. And at genus 1, this has been done by Brödel, Dua, Dulat, Tancredi, and Penante. And yeah, the same kind of dictionary needs to be set up for a higher genus. I think it will be easier to do this in the hyperelliptic locus. Well, at genus 2, this is no constraint. But starting from genus 3, you need to be very careful whether you're on the hyperelliptic divisor or elsewhere in moduli space.
I think in view of time, we should move on. So let's thank Oli again, and we'll move to the next speaker. Thank you.